Hello everyone, let's come to the fourth subsection, Hermite Interpolation. Now we will introduce you another interpolation method named Hermite. So this is different from Lagrange Interpolation and Lagrange Interpolation. Okay, if you remember, in the beginning of this chapter, we talk about the general interpolation conditions. In some cases, we need to also consider the interpolation conditions with derivatives at some nodes. Then this problem is called the Hermite Interpolation problem. Okay, that means we are given the function values and the derivatives of fx at some, for example, s different nodes, x1, x2 to xs. By the Lagrange interpolation or Lagrange interpolation, it means we only use function values. But now we need to also use derivatives. Okay, so here, at x1, we have, for example, function value, first order derivative at x1 up to alpha 1 minus 1's order derivative at x1. Okay? For example, we are given fx1 and f prime x1 function value at, okay, I write here. Okay, x1 here. And we are given the function value, and also we know the tangent line, the derivative, okay? And we are given another point, x2. We also consider function value and some derivatives. Of course, here the order may be different, and maybe we can choose fx2 and f prime x2. That means we are given another point here and a tangent line. Okay, so that means we need to find a simple function, okay, passing through the 2 points and start from this point with the tangent line. So like this, okay, like this. Okay, so and also for xs, we have function value in first order derivative up to alpha s minus 1's order derivative at xs. Okay, this is general cases, right? A general case. So that means we have how many conditions? Now, at x1, we have alpha 1 conditions. At x2, we have alpha 2 conditions. At xs, we have alpha s conditions. So here, okay, we compute the summation alpha 1 plus alpha 2 plus 2 alpha s. If we denote the summation equal to n plus 1, that means n equal to the summation I from 1 to s, alpha I and minus 1, then we know n means the degree. We need to find a polynomial Pnx such that, okay, its degree is n and satisfying, okay, the interpolation conditions. That means Pn, okay, mu i's order derivative at xi equal to f mu I, mu i's order derivative at xi, okay, or we write by yi mu I. Okay, mu I means the order of derivative, I from 1 to s, and mu I can be from 0, 1 to alpha I minus 1. Okay, so that means, for example, we are given, okay, function value and the first order derivative at x1 and xx2. Okay, of course, this is a more complicated case, right? So here, I just introduce you a simple case, not so complicated. Okay, so we only consider the case of s equal to 2. That means we only consider 2 points, and alpha 1 equal to alpha 2 equal to 2. Okay, that means we only given 4 conditions. fx1 and fx1 prime, fx2 and f prime x2. It's okay? So we have now four conditions. So n should be equal to 4 minus 1. It is 3, right? You should remember the degree of the polynomial equal to the number of conditions minus 1. Okay, so that means we need to find a cubic polynomial. Okay, so we denote it by P3x, so equal to fxi multiply aix, I from 1 to 2, and we use f prime xi, the first order derivative at xi, I from 1 to 2, each derivative multiply another function bix, okay? So that means, okay, aix and bix are also cubic polynomials. Okay, so that means P3x. Okay, of course it is similar like C1 plus C0 plus C1x plus C2x square plus C3x cubic. This is a cubic polynomial, but we don't use this form because we need to solve linear system to obtain the four coefficients C0, C1, C2, C3. Then this is not interpolation formula. Interpolation formula means we only need the function values fx1 multiply a basic function a1x plus fx2 multiply a2x plus the first derivative f prime x1 multiply b1x plus f prime x2 multiply b2x. It's okay? So that means we want just use the interpolation conditions, the function values and the derivatives, each value multiply a polynomial. Here a1, a2. A means the basic polynomial corresponding to function values, and b1 and b2 are corresponding to derivatives. It's okay? So just like we use Lagrange interpolation basis, right? So if we use Pnx, we review I from 0 to n fxi multiply lix. Okay, remember, if we consider the Lagrange interpolation formula, then li are the Lagrange interpolation basis. Okay, so here we need to determine the four bases, right? a1x, a2x, b1x, and b2x. Okay, do you remember how to determine Lagrange interpolation basis? Lix. Okay, we use the property. Remember, Lixj equal to delta ij. It's okay? That means when I equal to j, then delta ij is 1. Otherwise, delta ij is 0 when I is not j, right? Okay, so by these properties, okay, we can construct Lix. Okay, similarly, here, we need to consider the properties for the basis, right? So here, because a1 is the basic function corresponding to function value fx1, so the property is aixi equal to 1. But the derivative of ai at xi is 0. Okay, and aixj equal to 0 when I is not j, right? And the derivative ai prime xj is always 0. Okay, I and j are 1 or 2. It's okay? And for B, we know because BI, B1 and B2 are corresponding to derivatives. So that means for function value at xi, x1 and x2, the function value of B1 and B2 should be 0. So BI xi equal to 0. BI prime xi also should be 1 because this for the derivative. Okay, and BI xj should be 0, and BI prime xj, the derivative at xj is 0. Okay, and also ij equal to 1 or 2. Okay, I explain to you. Now you see, because if we substitute x by x1, then equal to fx1 a1x1 plus fx2 a2x1 plus f prime x1 b1x1 plus f prime x2 b2x1. It's okay? We substitute x here by x1, 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 x1 here. Okay? Because we want P3 satisfy the interpolation condition. That means it is equal to fx1, right? Equal to function value fx1. Here already fx1. So that means we need a2x1 equal to 0, b1x1 equal to 0, b2x1 equal to 0, and a1x1 equal to 1. It's okay? So that means we need a1x1 equal to 1, but a2x1 equal to 0. Okay? And b1x1 equal to 0, and b2x1 equal to 0. It's okay? So compare. Now you see 1 and 1, I and I, the same in subscript, then the function value is 1. Otherwise 2 and 1, different I and j, function value is 0. Okay? And for B, b1x1 is 0, b2x1 is 0. So that means for bixi is 0, bixj is 0. Okay? These four conditions. Okay? This is for the function value. If we check the derivative, okay, then the derivative I write here. Then P3 derivative should be, okay, f x1 a1 prime, right, derivative, plus fx2 a2 prime x, right, and plus f prime x1 b1 prime, right. You need to compute derivative, then derivative and derivative, okay, plus f prime x2 and b2 prime x. It's okay? This is derivative of P3. Okay? And if we consider the derivative at x1, then it should be the derivative of f at x1. Then here x1, here x1, here x1, and here x1. Okay? And now you see here already the derivative fx1, f prime x1. So we need, we need b1 prime x1 equal to 1. Is okay? And b2 prime x2 equal to 0. This term should be 0. And also this term and this term and this term, they are zeros. So a1 prime x1 equal to a2 prime x1 equal to 0. It's okay? So that means here ai prime xi equal to 0, ai prime xj equal to 0. You see? 1 and 1, 2 and 1. Okay? Different also 0. And for bi prime xi, then here b1 prime x1 equal to 1. So here is 1. But b2, oh sorry, here should be 1, not x2. Okay, should be x1. Okay, b2 prime x1 should be 0. You see, I and j also derivative is 0. It's okay. So we can obtain these 4 conditions, properties for the basis. Okay, so by these properties, okay, we can construct the 4 polynomials a1x, a2x, b1x, and b2x. Okay, this part is a little complicated, so I omit the detail. I only show you the result. Okay, of course. Okay, for you, I hope you can understand. And also, if you will use the Hermite interpolation by derivatives in your research, I hope you can know, okay, this method. Okay, of course, for examination, I don't test you for Hermite interpolation. I just interest to you this method. Okay, that means in many numerical analysis, we need also deal with derivatives. Okay, so now by the conditions of the basis ai and bi, we can obtain okay p3x by, now you see the form, okay, the condition fx1, okay, multiply this basis is a1x, okay, a1x, and plus the derivative of f at x1 multiply b1. This is b1. Okay, so this is a1x, and this function is b1x, and also plus, okay, fx2 multiply this function is a2. a2x, and this function is b2x. Okay, so now you say for a1x, it is equal to 1 minus 2 multiply a ratio x minus x1 divided by x1 minus x2 multiply x minus x2 divided by x1 minus x2 square. Okay, now you say for a1 and a2, just substituted x1 by x2 and also interchange x1 and x2. So you see x1 to x2, x1 to x2, x2 to x1, and here x2 to x1, x1 to x2, x2 to x1. Okay, from A1 to orbital A2. And now also B1 is x minus x1 multiply x minus x2 divided by x1 minus x2 square. And then interchange x1 and x2, you see, from x1 to x2, x2 to x1, x1 to x2, x2 to x1, interchange, then you will obtain b2x from b1. And also plus, okay, fx2 multiply this function is a2x, and this function is b2x. Okay, so now you see for a1x it is equal to 1 minus 2 multiply a ratio x minus x1 divided by x1 minus x2 multiply x minus x2 divided by x1 minus x2 square. Okay, now you see for a1 and a2 just substituted x1 by x2 and also interchange x1 and x2. So you see x1 to x2, x1 to x2, x2 to x1, and here x2 to x1, x1 to x2, x2 to x1. Okay, from A1 to orbital A2. And now also B1 is x minus x1 multiply x minus x2 divided by x1 minus x2 square. And then interchange x1 and x2, you see, from x1 to x2, x2 to x1, x1 to x2, x2 to x1, interchange, then you will obtain b2x from b1x. It's okay? So you only need to know this is a Hermite interpolation formula, okay, for two function values and two derivatives. So we can obtain a unique cubic polynomial denoted by P3. Okay, so that means here I show you from this point tangent line and to this point tangent line, then you can obtain a unique cubic polynomial. Okay, like this, passing through the 2 points with the same corresponding tangent line. Okay, this is a popular and famous the cubic Hermite interpolation polynomial at 2 nodes. Okay, and actually we use 4 interpolation conditions. That means P3 at xk equal to fxk, and the derivative P'3 at xk equal to derivative of f at xk. And here should be k should be 1 and 2, because here we use x1 and x2. Okay, we use x1 and x2, so here should be x1 and x2. Okay, this is a Hermite interpolation, the cubic Hermite interpolation for 4 conditions: 2 function values, and 2 derivatives. Clear? Okay, this is Hermite interpolation formula.